Well, since we are recording it, and this is everything's in the virtual world, so we don't have to wait for people to navigate an entire show floor. And because this slide just makes me feel like, it's so sunny out now that Wi-Fi 6 is here. It's bright, it's wonderful. I think we're going to go ahead and get started. And let's get this. Helps if I can click on things. Boom. All right. Everybody will be muted until the end of the webinar. If you do have questions, I highly recommend using the chat box. I welcome any and all questions. Hopefully we'll have enough time at the end to answer all of them, but if not, I will respond to each question individually. And so please do not hesitate to ask them. And the webinar is being recorded, so at any point in time, once we'll provide a link and you can watch it again and again, or never, however you feel you need to, but either way, it is being recorded. For those of you who I haven't had a chance to meet in the last 20 some years of doing CDO, my name is Nathan Holmes. I'm the Director of Training and Development here at Access Networks. I have been in the industry a very long time. There's a number of the certifications I have on the screen. These are more the network-related certifications, but I was an integrator for years. I was a manufacturer's rep. I've owned companies. I've worked all across the country in different places. So I'm a big fan of getting as much education as you can. Our customers look at us as being experts, so please try to be that for them. I also sit on CEDIA's Tech Council, trying to help guide CEDIA in the right ways to increase and improve their educational offerings to be relevant. And again, I taught another course at CEDIA this year, so I'm glad to be a part and a deep part of the industry in any way we can. Access Networks, for those of you who don't know, we provide industry-leading, enterprise-grade networking solutions for the modern home. We have both distribution products that you configure, and we have custom network design and support. Our IT team is certified not only in IT, but they understand the AV industry. So when it comes to troubleshooting and having insights that are relevant to you, our team, in my experience, has been second to none. I was Access Network's second dealer. I've been working with the company for over a decade, and I've been on the team now for 5 years, and it has been a great ride. And I think if you're not an Access Networks dealer, please talk to me. I can give you lots of reasons why you should be. Overall, why are we here today? We're here because Wi-Fi 6 is here. And the client devices, iPhone 11, Samsung S20, all these things are already available to use Wi-Fi 6. So it's important that we design networks for our customers that are using Wi-Fi 6. But it's also important to understand this is the first time Wi-Fi has been redesigned from the ground up, and it is fundamentally different. So we're going to talk about some of those different things and show you why it's not just about speed, it's about efficiency, and why you really should be already installing Wi-Fi 6 APs. To do this, we're going to start off with looking at why do we have a new name? What was the reason for that? Why do we need it? Then we'll talk about what's similar in Wi-Fi 6 to the previous generations, and that'll allow us to easily understand what's different, and then finish up with, okay, cool. That's what's different, that's what's the same, but what are my real benefits and realities that we're going to face, and how soon am I going to face them? That's what we're going to talk about. So what is generational Wi-Fi? Why do I need a new naming convention? Well, generational Wi-Fi was developed by the Wi-Fi Alliance, which is a nonprofit organization which tests devices to verify that they meet or exceed different characteristics of the 802.11 standards. Now, it was, when you look at it, 802.11ax, AC, N, G, A, B, this is super confusing for customers and clients. So generational Wi-Fi was designed to make it easy for manufacturers to go, yo, I got stuff that's Wi-Fi 6. You got stuff that's Wi-Fi 6? Cool. We know we interoperate. And by getting certified, you can actually get the Wi-Fi Alliance to give you certifications, but it also makes it easier. So, if you're Wi-Fi 6, it's really 802.11ax. Wi-Fi 5, 802.11ac, and Wi-Fi 4, 802.11n, which is a lot easier for a customer to understand because they're already, accustomed to that on their phone. 3G, 4G, LTE, 5G. Well, guess what? I want one better. I want Wi-Fi 6. It's not really one better than 5G, but it is something new. And having an icon on the screen to show you at what generation of Wi-Fi you're connected at could be really cool to help customers, come back to you and say, hey man, I need more Wi-Fi's. I need, the 6 up here. I only have a 5. How do I get the 6? and having a logo on a box that said it's Wi-Fi 6 certified really helps too. Now, what does that mean? Well, the Wi-Fi Alliance put a whole bunch of things together to, basically they're just testing to make sure that you meet the 802.11ax standard to be Wi-Fi 6, but it's also designed to give you an understanding of how you're connecting. So if you're on a Wi-Fi 6 AP, but you're only connecting at Wi-Fi 5, or you're connected to a Wi-Fi 5 AP, the idea is change the symbol and show what you're connected at. Because right now, if your client is connected to a 2.4 gig signal and you're not using a Wi-Fi 6 AP, guess what? They're connected at Wi-Fi 4. Wi-Fi 4 is from 2009. You really want your customers connecting on a technology that's 11 years old? Nah. So they made sure that to be Wi-Fi 6 certified, you have to have a user interface icon that shows you how you're connected. And they developed things that are real easy, but they still made it open for manufacturers. You choose what you want. And if you want a Wi-Fi 6 certified logo, just talk to the Wi-Fi Alliance, get them tested, and you can put down that you're Wi-Fi 6 certified. So it's a marketing campaign that really makes a lot of sense. It makes it easier to understand for consumers and for us. Now, to understand what's different, we have to start with what's the same, right? So we're going to talk about dual band support, channel bonding or channelization, some, what the heck is QAM and why do I care about it, and what's a modulation encoding scheme, and then something about spatial streams and which ones, which technologies with spatial streams actually give us benefits. So 2.4 and 5 gig. This is great because Wi-Fi 6 will be only the second standard that supports both 2.4 and 5 gig. Now, keep in mind, you're still going to design your networks on 5 gig coverage because you always use the smallest cell area to design your coverage, because you can always reduce a 2.4 gig cell size or individually turn some 2.4 off on certain APs. You can't add more coverage for 5 gig. So you need to always do your design on 5 gig coverage. And keep in mind, it's a smaller coverage area. So when we had Wi-Fi 5, you were able to do 1,500 square feet per AP. But with Wi-Fi 6, you've got to have a minimum of 3 dB and actually 6 dB more for the highest data rates. So you're going to drop down your coverage areas to not more than 1,350 square feet per AP. So basically, never put your APs farther than 40 feet apart line of sight. And if you're going into an older installation where Wi-Fi 5 was, understand you may not be able to hit your highest data rates if your APs are spaced farther apart than what they should be for Wi-Fi 6. So we're also going to continue channel bonding. Now, channel bonding is where we take smaller 20 megahertz wide channels and combine them together for basically a bigger lane of a highway. So basically in the 5 gig, we can take a 20 megahertz bonded to a 40 megahertz, which takes our data rate from 287 to 573. That's a doubling in data rate. That's awesome. We can go to an 80 megahertz wide channel and we go up to 1.2 gig. Now keep in mind, these are your typical 2 spatial stream data rates, which say an iPhone 11 would see. And according to the standard and possible capabilities, it says I should be able to go to a 160 meg channel with a 2.4 gig connection rate on an iPhone 11. That's insane. It's also not going to be feasible or possible because Wi-Fi 160 megahertz channels are not viable for use right now. Okay, so your current maximum channel width that you are recommended for design characteristics is an 80 megahertz wide channel, which means your iPhone still could connect at 1.2 gig on 5 gigahertz, which means your throughput, you always estimate your Wi-Fi throughput to be about 1/3 of whatever your connection is. So your customer is going to see about a 400 meg throughput, which is awesome from Wi-Fi perspective. So, but that's about what you're going to see. Now, the reason for this is because of interference. This is why we can't use 160 meg channels. And I like showing it this way because I think it really clarifies why it's important to consider which APs you're choosing and how they function. So consumer APs and a lot of prosumer APs are only able to use the Uni 1 and Uni 3 channels, so the low and high 5 gig. We know that we always have to use non-overlapping channels so that our Wi-Fi doesn't interfere with itself, right? Okay, that's going to cause problems. So if you're using consumer or prosumer APs, you only have 2 channels to choose from in 5 gig if you're doing an 80 megahertz wide channel. So if you get to 3 APs or more, then your Wi-Fi is absolutely interfering with itself. So we got to go to 40 megahertz wide channels if you're using consumer APs. Well, that means we can't even hit 1.2 gig. That means our maximum connection for a client device on 5 gig is still only going to be 574, which drops our throughput down to less than 200 meg. How do we combat this? Well, we use enterprise grade APs. They can use all the channels, Uni 1, Uni 2, 2 extended, Uni 3, which gives us up to 6 80 megahertz wide channels. That's awesome. So we don't need to do spectral reuse until we get to 7 APs. But it also means we still can't use 160 meg channels. One, because they go from standard channels to DFS channels to weather radar channels, and that just doesn't work well. But additionally, there's so much interference with other devices on the lower 80 gig channels or 80 meg channels, you're going to have issues. So just from a standard, don't ever use 160 meg channels right now, which means 80 megahertz channels are the maximum you're going to use currently, and you're going to use them in 5 gig. Now, for those of you, I'm going to answer the question now because I'm sure some people are going to ask it. Wi-Fi 6E. So Wi-Fi 6E was recently introduced by or approved by the FCC, and this was 1.2 gig of bandwidth, primarily in the 6 gig spectrum for use with Wi-Fi 6 only, meaning we don't have to deal with all those legacy data rates. And it means that we could technically use up to 760 meg channels. Now, this is probably not going to come out for, probably till 2022, until we really start seeing any devices. So you're still years off until this really becomes something to consider. But at that point, we might actually be able to start seeing some of the higher data rates that the standard is capable of. And I don't really, you're going to manufacturers that call them tri-band APs. I guess they kind of are, but because it really just kind of extends 5 gig all the way up into 7 gig, I just look at it as these are just more channels we can use, and you will eventually start using system designs that leverage these. For now, just keep in mind your highest throughput is going to be on 5 gig, even with Wi-Fi 6, but it's going to use 80 megahertz wide channels, and you should use enterprise grade APs to mitigate all of your co-channel interference and co-channel contention. Now, that doesn't mean that you don't still use 2.4. In fact, the 2.4 gig spectrum, this is the first redesign in over a decade. So it's absolutely going to work better than it has before. And I think this is one of the biggest reasons that manufacturers will also start using Wi-Fi 6 chipsets in IoT devices. So from a channel bonding perspective, it is still written into the standard to be able to go from a 20 to 40 meg channel, which could technically give you 574 meg. But because of co-channel interference and contention, do not ever use 40 megahertz wide channels on 2.4, and don't allow a manufacturer to tell you that's what you should use. Don't use manufacturers that are going to do that, because not only are you reduced to a single channel that can be used without interfering, but you're also going to be flooding all of the 2.4 gig around you and interfering with neighbors, all those things. It's just a bad scenario. So when it comes to 2.4, you're going to stick on 20 megahertz wide channels, which means your highest data rates are going to be on 5 gig, even though your coverage areas on 2.4 gig will be significantly larger. And that's great for outside, because we're not worried about data rate, we're worried about connectivity. All right, that's enough about channel bonding, but I want to talk about 1024 QAM now, because everybody always goes, well, how much faster am I going to get with my new Wi-Fi standard? Well, the speed really comes in because of the QAM rating. And it is going to be a little faster, but that's not really the big driving force behind Wi-Fi 6, but we are going to get some benefits. So what QAM is quadrature amplitude modulation. We take two waves, they phase shift them against each other, and where they interact is a point in space. And depending on how many bits and points in space we have determines how much data we can send each transmission. So 64 QAM was used for many years. And then with Wi-Fi 5, we went up to 256 QAM. Well, this was pretty awesome because it sent a lot more data, but it also, the space between the bits got a little smaller. Well, guess what? Wi-Fi 6 is going to jump that to 1024 QAM, but it's going to even be smaller, that space between each of those bits. And that's an important thing to consider, because as that space between those bits, or those points of contention between two waves, as that decreases, then you need clearer and clearer signal to be able to differentiate where those two waves are interfering. So basically, you need better signal compared to the noise in the environment. I like to look at it this way. If I gave you a target and I put it 1 foot away from you, pretty much every time you could throw a dart into that target and hit it. You're not going to be in the center every time, but you're going to hit that target, right? What if I move the target 20 feet away from you? I don't think I could hit that target. Now, think about how hard it is to hit one specific point in a 1024 QAM installation. Even if you were 1 inch away, it'd be hard. Go to 1 foot, 10 feet, 20 feet. Imagine how hard that's going to be. It's going to be super hard. In fact, it's likely that your client device will have to be significantly closer than it was previously if you're going to achieve 1024 QAM data rates. How close? Well, your client device is probably going to be within about 22 feet of that access point to be able to achieve what's called an MCS rate of 10 or 11, which means the signal to noise ratio is sufficient enough to achieve 1024 QAM. Now, that doesn't mean you can't be connected farther from the access point. You'll stay connected. What you'll see in this chart, you'll drop down in your QAM rating, so how much data we can send each time, which means your overall data rates decrease significantly. So you need to be within 22 feet of the access point for your highest data rate, which means your AP coverage should not exceed 1,350 square feet per AP in multiple access point Wi-Fi 6 deployments. Now, why is that? Well, when you look at designing your coverage on 5 gig, in designing with being within 22 feet of an AP, you also have to have a minimum of 20% overlap between adjacent access points. And you can see in this diagram, it is critical to put each of your access points on different channels so they don't interfere with each other from a co-channel interference or co-channel contention standpoint. This will allow your devices to seamlessly roam between your access points. This is one of the most important parts of your Wi-Fi design, is ensuring that your APs are never more than 40 feet apart, line of sight, with you want 20 to 40% overlap between your access point, and you must use different channels. Now, keep in mind, this can change. If you've got a gym with mirrored walls, guess what? You may need to go down to 1,000 square feet or less per AP. Mirrors are horrible. E-glass, almost 100% mitigation of RF energy. Stone, metal. The construction materials in houses is going to change this design criteria a lot. And you want your APs close, but not too close. And you also don't want them sharing, like, say, a hallway together and things like that, because you're going to get, multi-path, increases and decreases. So you want them, I always try to recommend to wire every closet, pantry, any out of the way place we can put them. And then understand there are going to be places where if you want right coverage, you're going to put an AP in the room and help your client understand why. The smoke detector is not going to go in a closet. So they're going to use that smoke detector, hopefully never. They're going to use their Wi-Fi every single day. You might want to put it in a space where it's going to perform the way they expect it to. Overall, don't put your APs more than 40 feet line of sight apart when you're doing Wi-Fi 6. Okay, enough preaching. MIMO, or actually spatial streams. When we talk spatial streams, the one thing we think of most often and we hear about in literature most often is MIMO. The idea of taking multiple spatial streams, taking the data we're going to transmit, breaking it into smaller chunks, sending it out multiple antennas at the same time to be received by multiple antennas at the same time, and then put together at the client device. Well, guess what? Wi-Fi 6 is going to keep using MIMO. In fact, it's now increased up to an 8x8 MIMO standard. If you're transmitting at the highest possible data rates with an 8x8 client, you could see, and this is all theoretical, mind you, a 9.6 gigabit data rate. Now, I mean theoretical because I've never in my life seen a client device that has more than 4 spatial streams. 3 is rare, 2 is where most everything is. So the maximum data rates you're probably going to see would be a 4-stream device connected at 80 megahertz, so 2.4 gig. Realistically, most of your data rates are going to peak out at 1.2 gig with about a 400 meg throughput. Either way, that's the benefit MIMO and channel bonding or channelization give you. And this is very real, and you'll see it all the time. Multi-user MIMO, we hear about in manufacturer literature constantly. Guess what? What is it supposed to do? It's supposed to take each of those spatial streams that are available and potentially send them to different clients. And they've worked that better in Wi-Fi 6 to provide both upload and download. So in Wi-Fi 5, you can only download to multiple clients. Technically, in Wi-Fi 6, you're capable of transmitting both in an upload and a downlink capacity to and from clients, and you could use up to 8 spatial streams or a maximum of 4 spatial streams per client. This is true. The technology is developed. It exists. The reality is multi-user MIMO really doesn't work. MIMO does, but keep in mind, like on the data rates, you're reduced to mainly 2x2 radios. So that's going to be where you see most of your data rates. Multi-user MIMO, look, there's currently no devices out there at all that support Wi-Fi 6 multi-user MIMO uplink. When it came to Wi-Fi 5, there were a few clients that supported it with Wave 2, but then most manufacturers turned it off because it crushed battery life. Secondly, of the clients that did exist, many dual antenna clients had to switch to single stream mode, so it automatically didn't give you any performance increase. And it also requires the use of transmit beamforming, which requires sounding frames and a bunch of other things. So here's this technology that's supposed to help you get better throughput in super high density applications. One, none of our houses are super high density applications. Two, all the technology that causes it to work reduces throughput so significantly that you're actually reducing performance by using multi-user MIMO. So therefore, client devices support it. So even though an AP does and can, doesn't give you any benefit. So be aware of that. MIMO does give you benefit, and I'm telling you right now, there's going to be some cool things in Wi-Fi 6 that also give you benefit. This is going to be awesome. So 3 things we're going to discuss that are new and are awesome. OFDMA, orthogonal frequency division multiple access. I like that, multiple access. It's going to be cool. SSID coloring, which, no, I was hoping, yeah, Wi-Fi in the air, it's different colors, it's bright. Nope. It's going to be something different, but it's going to be also be cool. And then we're going to have these target wait times. So let's look at this, because these are all new things, and it definitely makes Wi-Fi 6 different than any Wi-Fi previously. Now, it is called high efficiency Wi-Fi for a reason, and OFDMA is one of the biggest reasons for that. Prior to Wi-Fi 6, Wi-Fi transmissions used OFDM, orthogonal frequency division multiplexing, and all transmissions were one-to-one in nature. That means when a client device was transmitting, didn't matter if it was sending a little bit of data or a lot of data. It always used the entire channel bandwidth. Doesn't matter if you designed for 20, 40, or 80 megahertz. It was using that entire bandwidth for small transmissions, large transmissions, whatever. It had to use the whole thing. That's how OFDM works. That meant your access point can only transmit or receive from a single client at a time. You know, in this example here, what do I have? 7 devices all connected to the AP? Great. One talks. The AP and 6 devices listen. The AP responds. All 7 devices listen, because you have to use the whole channel the entire time. Now, that's not very efficient, because let's face it, we got a lot of IoT devices that do little bits of data, and a lot of times we're just trying to stay awake. So OFDMA is something we really borrowed, or is borrowed from the cellular world, and it's the idea of breaking up the spectrum into smaller resource units called tones, and allowing a client device or an AP to only use the number of resource units it needs for the given size of the payload being transmitted. Not only does this mean I only have to use the spectrum I need for my transmission, but it means multiple devices could share in that whole spectrum use. Now, this is different from multi-user MIMO, where you're dedicating an entire spatial stream and a whole transmission time. I'll show you what I mean. So in legacy OFDM, you can see on the example on the left, user 1 uses that whole channel width, or sorry, user 0, then user 0, then user 1, then 2, then 3, then back to 1. So each transmission, each user has to, it capitalizes the entire channel width, all of the available subcarriers. And with OFDMA, you can see in this example, we're transmitting between 1, 2, or even 4 clients simultaneously by dedicating different subcarriers to each of the devices when they need it, which is really awesome. It makes it a lot more efficient. To do that, there were some fundamental changes that had to happen. So in Wi-Fi 5 and before, your channel was broken up, a 20 megahertz channel was broken up into 64 subcarriers. Okay, that was great, and it did its job. Well, with Wi-Fi 6, we actually broke it up into 256 subcarriers, which means on an 80 megahertz wide channel, you're actually using 1,024 subcarriers, or on 160, over 2,000 subcarriers simultaneously being used, depending on where they're being transmitted. And what we do then is we group those subcarriers or resource units together in what we call a tone. And we have various sizes based on how many subcarrier channels are bonded together. Makes sense. If we need to send more data, we use more subcarriers. Less data, less subcarriers. Okay. So in this example, you can see the smallest tone is a 26 resource unit tone. So basically, we're dedicating 26 subcarriers to that particular conversation, that payload. Well, if we did that, we could technically talk to up to 9 clients. Well, that's great if you're doing little bits of data, but let's say we need to do a little bit more. Well, if we're doing 52 resource unit tones, so 52 subcarriers, we could do 4 clients. 106 gives us 2 clients, or if you get a client device that's sending a whole bunch of data, it just uses all 242 carriers, subcarriers in that particular 20 megahertz wide channel. So it's dedicating at that moment in time the entire channel to one transmission. Okay, cool. Well, because we've actually designed through channel bonding wider channels, what that actually correlates to is in our 80 megahertz wide channels, which is our maximum channel width designs, we could technically transmit from between 1 to 37 clients simultaneously based on the amount of bandwidth needed to transmit to that particular client at that particular time for that particular payload. And your AP will dynamically shift and adjust that based on the request to transmit and receive and utilize it the most efficient way. And keep in mind, there'll be many times where it may stay with OFDM just from a legacy perspective, but as more and more clients become Wi-Fi 6 capable, it will be able to use less and less of the frequency to one particular conversation and really have multiple conversations or more efficient conversations happening on a regular basis. This is really cool. Now, SSID coloring, I think, is going to really help a lot of our integrators that are working in, New York, any cities that have, these high density of people in a given area that are using Wi-Fi. This is because Wi-Fi in general and by design uses something called carrier sense with multiple access collision avoidance. Basically, Wi-Fi is sharing the air. So all of the devices in a given area are all fighting to use the air at any given time. To prevent interference, the way Wi-Fi works is no 2 devices can use the same frequency, so the same airspace at the same time. So what has to happen is before a client device can transmit, it has to go, hey, anybody else transmitting right now? Because I really need to, and if nobody else is, I want to. And that's how it works. And if you're on a single access point in the middle of nowhere, you're 20 acres and the house is in the center and there's no RF energy around, man, the only thing you're fighting with is other devices in the same house trying to use the same AP at the same time. But that's not really where we tend to play. We tend to play in houses that use, multiple access points, or we're in MDUs or things where you got tons of people around it or tight-knit communities. Your Wi-Fi is interfering with your neighbors and their Wi-Fi is interfering with yours. So here's a typical example. I've got a 4 AP installation, or maybe 3 APs are in one house and AP4 is in another house. Either way, I've done proper wireless design. AP1, AP2, AP3, they're all on different channels. I'm using 1, 6, and 11, the only channels available for 2.4 that are non-overlapping. But once you get to that 4th AP, or maybe it's a neighbor's house, it's a 4th AP, so therefore there's not 4 available channels. So you're absolutely going to have more than one access point on a given channel. When that happens, if AP1 goes to transmit on channel 11 and it hears the preamble from AP4 transmitting, AP1 has to wait because it goes, ooh, that channel's already being used by AP4. Same thing for a client device. If that iPhone there was trying to communicate back to AP1, which it's authenticated to, but it hears a transmission from AP4 or one of AP4's clients, it has to wait because no 2 devices can transmit. And you can kind of see it here, but imagine this. Here's another scenario where APs 1 and 4 are really far apart, but the client device connected to AP1, if it can still hear AP4, or a client connected to AP4, when it goes to transmit, if there's already somebody using the airspace, it has to go, man, I can't transmit right now. The airspace is in use. I have to wait. So this is why you can have applications where maybe you're in your backyard, you're using your Sonos, it works great, and then all of a sudden you can't control it at all. And you notice your neighbor just put in a new Wi-Fi camera outside that's blasting on 2.4 on one channel all the time. You're all fighting for the same airspace. Change to a different channel, something like that. That's how you had to do it with Wi-Fi 5 and earlier, because there was no way to stop that. You literally were all fighting for the same airspace. So with Wi-Fi 6, they introduced something called spatial reuse, which is an idea of adding a number, from 1 to 63, it's added to the PHY header of the 802.11ax or Wi-Fi 6 frame. And this color number identifies the basic service set that the client device is connected to. So if I go to transmit and I hear another device broadcasting with the same color bit, I'm going to assume that, oh, that's probably another client device connected to the same API I am, or something along those lines. So it knows I can't transmit because in its mind, in the client's device mind now, it says, ooh, we're both connected to the same thing, same color bit. Nope, can't transmit. I've got to wait because I can't transmit with another device that's using the same color bit at the same time. But what if you hear a different color bit? Well, then it goes, hey, can I transmit? Oh, wait, I hear something. Oh, wait, that's a different color bit. I know for a fact that's not the API I'm connected to. Couldn't even be a different network, whatever. I'm going to go ahead and transmit anyways because I don't care. If it's a different color bit, it's going to go ahead and transmit. So imagine right now you're in a MDU, in a big city. You might be able to see 20 or 30 units. And if all of those units are all using channel 1, every device in all of those units are always battling with each other, and only one device in any unit can broadcast at the same time. This will significantly help that because most likely they'll all have different color bits and they won't have to wait. So you'll get rid of a lot of latency and a lot of the co-channel contention we're facing consistently now. All right, the last thing we're going to talk about, which I think is really cool because frankly, I'm always looking for better battery life. And target wait time was a power saving mechanism that was developed for IoT devices way back in 802.11ah. And the idea was, if we can allow devices to go to sleep and then wake up only when they need to transmit, we could significantly increase their battery life. And in fact, we've seen up to 67% increase in battery life. So what happens is your Wi-Fi 6 device is like, I don't have anything to say right now. I'm gonna go take a nap. And the AP says, sure, let me create a schedule. And this schedule works for multiple devices. So when that first device says, I'm capable of receiving a target wait time, add me the schedule, the AP does it. It just says, oh, okay, I got a target wait time enabled device. Let's create a schedule. A second device says, hey, I'm also able to use target wait times. Add me the schedule. The AP will create a master schedule internally for when each device should wake up. It will then transmit this schedule back to each of those client devices, indicating, yo, here's when you're going to wake up, go back to sleep. Here's when you're going to wake up, go back to sleep. That way, not only can the device sleep longer, but it also reduces the amount of transient interference because you have less time where the devices are going, hey, can I transmit? Can I transmit? Can I transmit? So we're getting rid of, intrinsic interference, and we're also saving battery life. Overall, this is a really, really cool benefit. I can't wait for it to go into use. All right. So that's Wi-Fi 6. There's other things in there, but I think those are some of the biggest and most important things to consider. Now, what are the benefits and realities? Well, generational Wi-Fi, I think, is really going to help clients understand why they need to upgrade to Wi-Fi 6, because right now they have no clue if they're connecting to 802.11n, and that's 11 years ago. And anytime your clients right now are on 2.4, they're connected at 802.11n. So this will help them go, man, I need new APs. I've got to be on Wi-Fi 6. Now, in the short term, we're going to have a lot of legacy clients, Wi-Fi 4 and 5, and they're still going to be able to connect, but the real benefit from speed is going to come for Wi-Fi 6 clients that can get the capability of 1024 QAM. But to do 1024 QAM, your planning is going to have to be a little tighter, less space between the access points. And that correlates about 1,350 square feet per AP. If you're doing just a retrofit of an old installation, an old site, keep in mind, you may need to either move some wiring, add some wiring, maybe add an AP via mesh. But overall, keep in mind, your APs are doing a lot more than before. So it's becoming increasingly apparent. Look at target wait times, SSID calling, all those different things are all handled by the AP. The better APs that you have, the better experience your customer is going to have. And it starts with the right design. Additionally, look, Wi-Fi 6 2.4 gig is the first redesign we've seen in the market in 10 years. large areas of coverage as always, but still much lower data rates. So don't expect to have all of the data rates we had on 5, but it is a better connection, a more efficient connection. And there was one other thing that was added. So IoT devices we find end up being installed right on the edge of coverage, very edge. They're out in the middle of the yards or backyards or down by the boat docks or any place we don't want to walk to. So we want a sensor there to figure out what's going on. That means we have a lot of problems with devices falling offline when they're on that edge of coverage. Well, there was another feature added in Wi-Fi 6 called a high efficiency extended range single user format, which allows for devices that are connected on 2.4 gig, primarily outdoors on the edge of coverage, gives a little boost to that header, to keep it connected when it's at its lowest data rates. So definitely going to be helpful for, I think, IoT devices, and a big encouraging factor for manufacturers to use Wi-Fi 6 board sets, even on 2.4 gig. Now, like I said, we still need to design for 5 gig, and you need to have higher signal noise ratio. Remember, client devices need to be within 22 feet to get the highest data rates, and should be even closer than that if you want the maximum data rates. Target wait time is awesome. I think we're going to see a much better battery life, and all these things are going to become more and more relevant as more and more devices are Wi-Fi 6 capable. I mean, right now you may have a fraction, 1, 2, maybe 20% at most of your devices are Wi-Fi 6. Give it a couple years, and you're going to have 60, 70, 80, 90% of your devices are going to be all Wi-Fi 6 capable. And then all these efficiencies really are playing and doing their part to provide the best experience for your customers. And I think this should show you why now it's important to already be installing Wi-Fi 6 and keep doing it. We'll do 6E a few years down the road when it becomes relevant. All right. So I think we just kind of went through all of this. But I'm going to put a shameless plug in. Look, we are announcing at the show, we have multiple Wi-Fi 6 access points under the Access Networks brand. We've got, from small, medium, high-end deployments. You've got, the A550, 650, and 750. They're all Wi-Fi 6 capable. They're all capable of mesh. They all have, patented technology for beamflex, things like that. And we've got a team that can help you understand what AP is going to be relevant to you, to your project, because different ones are going to be better. If you got a client that just wants the best, look, A750 was the first Wi-Fi certified AP out there. It is amazing, but it doesn't have to go on every project. The 550 and 650 are awesome APs, and for the right project, maybe the better choice, especially from a financial perspective. And if you don't have time during the CDS show to go to our virtual booth, you can always reach out to client services at accessnetworks.com for more info. From a sales perspective, from a technical perspective, training perspective, whatever you need, our team is here for you, and we want to help you in any way we can. All right. That was it. I hope it was helpful, but I want to open everything up to questions and see what we can do to help fill in any gaps that I might have missed.
Hey, Nathan. We have a couple questions. The first one from Joe. It's a great question. How do we talk in layman terms about Wi-Fi 6 versus Wi-Fi 6E differences? He's getting a lot of people saying they want to wait for 6E instead of upgrading now.
That's a really good question. So for those of you who don't know, the first Wi-Fi 6 access points were released 16, 18 months ago. So that means we've already had Wi-Fi 6 access points for almost a year and a half, closing in on 2 years. We're a year and a half to 18, call it 2 years out before we really start seeing any Wi-Fi 6E devices. So why would you, well, let's make another statement. You end up redoing your Wi-Fi, so improving your Wi-Fi every 3 to 5 years. That's just a reality. The standards come out, new devices come out, everything like that. If you're not putting Wi-Fi 6 access points into your designs right now, every single device that those clients buy for the next, 2 years is going to be handicapped. Additionally, none of the Wi-Fi 6 devices we have right now will be able to be upgraded to support Wi-Fi 6E. Wi-Fi 6E, both from a client perspective and an access point perspective, is going to be a hardware change. Therefore, it's a minimum of 2 years. It's likely 3 years plus before we start seeing a lot of Wi-Fi 6E capable client devices. That being said, that's already when you're going to want to look at upgrading your systems and moving forward. So Why would you want to spend $1,400 on a device right now and know that 2 years from now, when you're replacing the device, you still don't have the right APs to support that client device? So it's important to put Wi-Fi 6 in now. The client devices are here. We're using them. It's improving the performance across the entire network. And you're never going to buy something today and have it last for the rest of your life. The infrastructure you put in is critical to ensure that you can add new APs when they come down the road. And you don't have to replace the entire network either. It may be, 3 years down the road, Wi-Fi 6 is still sufficient for most of your devices, but in the kids' room where you've got some gaming, or the living room, maybe we've got some new, streaming technology, we could replace 1 to 2 APs and not have to redo the entire project, as long as you're using manufacturers that do that. So I personally, I could never go to a customer and say, you know what, I'm going to sell you a brand new 2016 Mercedes today. Well, why would I do that? Well, man, because I don't want to sell you a 2021. It's going to, 2023, there's going to be a better model. So I'm going to tell you the same thing that you've been using for the last 5 years, because, I don't want to sell you because there's going to be a new one coming out. That doesn't make sense. You are creating a relationship with your customer over time, and it's up to you to get them to understand this isn't a buy and forget. You are going to upgrade your system over time, period. So depends on how relevant you want to be.
Great answer. Another one I want to tie in is time. Since you did say time, I have a question from David D. He's talking about legacy devices will still be affected. So he won't see a gain for years to come, or yes? Or is there going to be a compatibility mode that helps with legacy devices in Wi-Fi 6? And it's in regards to SSID coloring.
Great question. The answer is no. A Wi-Fi 5 and earlier device doesn't have the capability to analyze the header in a Wi-Fi 6 transmission, which is what contains the color bit. So the only devices that will see this and be able to utilize this are going to be Wi-Fi 6 capable devices. And you have to think about how manufacturers in the industry from, client devices look at things. You're going to see every single ISP approaching every single one of your customers telling them, oh man, you have to have Wi-Fi 6. You have to have Wi-Fi 6. They're going to put Wi-Fi 6 capable routers and all-in-one appliances in there. If you're not putting Wi-Fi 6 APs, they're going to be telling their customers how much better than you they are. Additionally, you're going to see new devices from manufacturers like Wi-Fi 6 capable set-top boxes, Wi-Fi 6 capable streaming media devices. If your client devices don't support it, guess what? They're going to take your customer away from you. Yes, you are right. A Wi-Fi 5 device will not be able to benefit from Wi-Fi 6 technology. The answer to that is every single device in your home has a limited lifespan. Think about how we all years ago fought against touch panels being iPads. And now we tell customers, oh yeah, use your old iPad to be your touch panel. Even that is outdated. We think about things wrong. We are an industry of keeping our customers abreast of technology and having technology that performs better. There is a reason that Wi-Fi 6 was redesigned from the ground up. All Wi-Fi 6 devices will function better, and they're already changing it. Every new iPhone, every new Samsung, every new Android phone they're going to get will all be Wi-Fi 6 capable. All their iPads, their computers, their laptops, all these things are all going to be coming Wi-Fi 6. So over time, look, it's 2020. We had Wi-Fi 5 in 2014, 15? It took 3 to 4 years before the majority of all the devices were Wi-Fi 5 capable. It's still going to be that way with Wi-Fi 6, but you have to help your customers be able to support it now because their clients use it now.
Awesome. And then another question, I just want to kind of tie into your first answer when you talked about infrastructure. GJ asked a question, and it's a great question. Does any of the Wi-Fi 6 functionality rely on certain generation of hardwiring, Cat5e, Cat6, Cat6a, or Cat7?
That's a phenomenal question. So one, it's easy to go and be the lowest common denominator and say, oh, we only need this and it'll work, okay? I before I started in residential, I worked in commercial, and you always, design to the current standards, and engineers are hired to do that and make sure you meet standards. So in residential, the current ANSI TIA residential wiring infrastructure standard, the 570D standard, calls for category 6A cabling at all device locations to ensure capability of 10 gig connectivity. So from a standards perspective, that's what you should be using. Now, from a realistic perspective, the manufacturers of access points were very concerned about the cost of replacing all the infrastructure, especially in commercial buildings, schools, all these places where you've got thousands of category drops, and it's an exceptionally high cost to change them out. So the capabilities of each AP dictate how much possible bandwidth it can attain on its Ethernet port. And for example, in our access points, the A550 happens to be a 2x2 access point, which means if you did a 160 meg channel, you could technically be capable of a 2.4 gig connection rate. So, okay, that right there, even at, we know we're going to have about an 800 meg throughput max, but that's one direction. So you could see how one direction you could exceed a gig. What they've done is they've included things called N-base T ports or link aggregation groups where you can combine standard 5E or 6 to get multi-gig connectivity. But that becomes standard in your APs when you get higher, where there's two different approaches, or three different approaches. One, you put 10 gig ports on your access points and use 10 gig switches. Two, you put multiple 1 gig ports and use switches that are capable of using what's called a link aggregation group, where you combine those two ports to create larger trunks. Three, use something called N-base T ports, which are ports capable of achieving 2.5 or 5 gigabit connectivity over standard category 5E and Cat6 infrastructure. To use N-base T ports, you have to have N-base T switches and N-base T access points, but it allows you to attain multi-gig connectivity over existing infrastructure. That's the way, our access points were designed and function. We've got N-base T ports and switches that will also use that. But I also recommend wiring. If you're doing your wiring, you should be running Cat6A to all possible locations where you might need 10 gig connectivity. Cat6 will still give you 10 gig up to 50 meters, and it's easier to terminate. So when I recommend wiring houses, I always recommend running a Cat6 and a Cat6A to every access point, every TV location, all those things, because 6 is easier to terminate, easier to qualify, which you should absolutely be certifying and qualifying every single run on a project. And it's easier, it's more flexible, but by having Cat6A there, it's simple to put a keystone on the Cat6A at the time of deployment, certify the cable, and then you could easily drop in a Cat6A jumper at any point in time and utilize a 10 gig backbone if needed.
Awesome, Nathan. That's exactly what I was going to say, but I wanted you to say it first. At this point, is it possible for you to place your salesman hat on? Because I have a great question from Patrick Coleman. He wants to know, what's the main difference between the A650 and the A750 access points, besides the obvious, the number of antennas?
So part of it's the number of antenna patterns, because of the fact that there's some beamflex antennas and some omnidirectional antennas. Secondly, the 750 is a 4x4x4 on both 2.4 and 5 gig, whereas the 650 is 2x2 on 2.4 gig and 4x4 on 5 gig. The real big benefit when you get to that side of things deals with something called diversity. Most of your client devices are only 2x2 client devices. So you're going to benefit from 2x2 MIMO, but how do you get better signal? Well, if you've got twice as many antennas on the AP, so you got a 4x4 for a 2x2 client, diversity allows you to send out two different copies of the same transmission and allow the client device to receive whichever one it receives better, the client device chooses. So that's a quick diversity perspective. So not only do you go from 128 antenna patterns to 4,096 antenna patterns, which is like taking your voice and pinpointing it straight to somebody's ear, which helps you cut through, so much interference, much better connection rates. But it also gives you diversity, so your client device can choose from more patterns, which again, when you're talking 2.4 gig and you're at that edge of coverage, anything you can do to improve that is going to be better because it's about stability. So diversity adds a lot of stability. So when you're going from a 650 to a 750, you get diversity benefits, MIMO benefits, antenna pattern benefits, but it's also cost. You know, you've got a decrease in cost because you have a slight decrease in performance, but you're still getting 4x4 on 5 gig. You drop down to 2x2 on 2.4 and lower antenna patterns.
Perfect. And then I'm sure we're pressed for time.
We're at the last, this will be the last question.
Last question from T Cape. In a mixed 5 and 6 environment, Wi-Fi 5 and Wi-Fi 6, will a Wi-Fi 6 access point communicate with each device using its 5 or 6 capability over a given time, or will the AP drop everything to 5 communication? I know you kind of skimmed the surface on that one.
So depends on what's happening with the access point. And it depends on your Wi-Fi 5 client devices. So there are instances where Wi-Fi 5 client devices have outdated drivers. And because they haven't been updated, they have some compatibility issues with Wi-Fi 5 or Wi-Fi 6 access points. In those applications, you may need to run an access point in a compatibility mode where you've reduced or eliminated most of the Wi-Fi 6 features for compatibility to allow all devices to connect. The reality is, if you're not having a device out-of-date driver issue, things like that, and all the client devices can connect and transmit, the access point will dynamically utilize whatever it needs to for the transmission. So if most all of your clients are Wi-Fi 5 and using OFDM, then it will likely continue to, even on a Wi-Fi 6 client, use an OFDM scenario where the entire bandwidth is dedicated to that one particular Wi-Fi 6 client. As more and more Wi-Fi 6 clients become prevalent and you face situations where more than one device is requesting to use the channel at a given time, then it can begin to leverage each of the Wi-Fi 6 benefits as needed to ensure that each client device gets the most efficient Wi-Fi transmission at that given time. So it's designed to be dynamic, and it's designed to allow the access point to make all the decisions, which is why it's critical that you use the best access point you can, so it has the best processing power, memory, and capabilities to serve that environment. All right. Well, I would like to thank everyone for joining us today. They were great questions. I really appreciate it. I will respond to anybody who's asked questions we haven't had a chance to get to yet. We will reach out to you, but thank you again for joining us. My contact information for those of you who don't have it is my first name, last name @Access Networks. I can also be reached at clientservices@accessnetworks.com. Please pop by our booth. We've got our lounge there where you can ask any of these questions as well. I may be in there at different times along with Bobby and the rest of the team. And we look forward to seeing you there. Hope you have a great virtual CEDIA, and thanks for joining us today.